Okay. طيب. So let's start. Somewhere around here. So okay. طيب. So today is lecture 10. It's February 14th. Extra class weird أنا صراحة. I've been teaching since 2003. Weirdest class هذا from all aspects. Today يعني we'll continue with quantization, encoding. And one announcement, which is quiz 2 is on Wednesday, this coming Wednesday. بعد بكرة. And it will cover quantization of Gaussian sources that will solve a problem about today. It's very similar to what you will expect of the quiz on Wednesday. So make sure you focus on today's lecture. Wednesday. Okay. لا اللي بعده بعد الامتحان. انت بعد الامتحان. نحن for the rest of the class the day after tomorrow. انت بعد الامتحان. Okay. طيب. So نحن we left last time. We are talking about quantization. Okay. And in more specific, we are talking about quantizing a Gaussian source in an optimum way. Again, Gaussian source is very commonly used in communication as a reference for all analysis. Most common signals that you deal with are not Gaussian. And speech signal is not Gaussian. Video signal is not Gaussian, but Gaussian sources or Gaussian signals are usually used as a reference for studying the performance of many systems. In some cases, it's the best performance. In some cases, it's the worst that you can experience. So if you design your system to work with a Gaussian source, then it can work with any other source. Question? I can move it. Tutorials? And I will both last year. I taught this course 2 years ago and then long time ago. So I don't have the long time ago. I only have the midterm that I gave to the students 2 years ago. So I will upload that for you. Tutorials just solve problems from the book. Honestly, I don't have in mind any. Or search the web. I'm sure there are a lot of. But if you understand what for the quiz, if you understand what we will do today, for sure you should do well with the quiz. For the midterm, we'll talk about the midterm next week or the week after. Next week. طيب. In an optimum way. And the criteria, if we talk about optimization, whenever you have an optimization problem, you either maximize something or minimize something. So you have to have what we call the objective function. What do you want to optimize? I want to minimize your cost. You want to maximize your profit, to minimize your error. In this case, we want to minimize distortion. The one we talked about last time, which is mean square distortion. Which is what? Which is the expected value of the difference between the original signal and the quantized signal. Because when you quantize your signal, will not be exact. So this is your original signal, and this is your quantized signal. This is your original Gaussian signal, and this is the levels that you will quantize your signal to. So, for example, again, the shoes example. Why did they pick 37, 38, 39? Is this the best? Maybe somebody studied the sizes of feet of human bodies, and then they found out to round them to 37, 38, 39 is the best. It's closest. What does it mean? What does it mean the best? It's closest to most of the people. So when you buy a shoes and then you fit it or round it up, in this case you cannot round it down unless. And I know many families. They always buy a tight one that it will grow with time. By the time it fits you, it's old. So you have to buy a new one. Anyhow, or there are some other families who want long-term planning, so buy big ones so that lives with you. Again, when your foot grow, it's about time that you need to change it. So anyhow, so expectation, we know that. So this is Gaussian, then it's just Fm of m dm, and then this is the Gaussian medium. So what's good about this is that we don't need to solve this. People have solved this in two scenarios using uniform quantization and non-uniform quantization. And exactly what we are looking for here is we need to decide on those V's, the values of V. So if this is your whatever Gaussian distribution with zero mean and unit variance, sigma equals 1, then what will be those ranges that we need to decide based on how many levels we want to quantize to? If I'm looking for 2 levels quantization, then I only have 2 levels. So all numbers between whatever 0 and we'll give examples, and maybe it's not very clear for me. But based on how many levels we are interested in, I need to decide what are those exact values. And the tables that we started showing last time show exactly what we mean by this. So let me put the tables, and then we'll solve examples on them. So this is the uniform quantizer for a Gaussian source. Okay. And then this is the non-uniform. The Lathy's book does not have this. This is from Prowakis. But I always like to, as I said, Gaussian reference is very important. So I wanted to cover it. No. Gaussian source is like you go to MATLAB and type rand n. Rand n in MATLAB, it will generate a random number between minus infinity and infinity that follows the normal distribution between with zero mean. And if you do this, it will give you all kinds of numbers. So next MATLAB assignment, you will do quantization and coding for a Gaussian source. So is that a continuous signal that's Gaussian? Yes. Is there a Gaussian generator that exists that's an analog one? I don't know, صراحة. But yes, يعني in MATLAB you can generate. And if you generate 1 million and plot the histogram, it will be a Gaussian course. يعني just very simple. Put rand n of 1 million. That's it. بيطلع لك 1 million value. يعني histogram of this, you'll get a Gaussian. Yeah. Fine. So here we have two tables. We have uniform quantizer, non-uniform quantizer, and let me bring another small figure so that we have everything we need طيب maybe I will put this in the next page because okay. طيب first of all, generally, what do you expect to be better, the uniform quantizer or the non-uniform quantizer? Or what's the difference first? What's the difference between having a uniform quantizer and non-uniform quantizer? Anyone? Spacing between the levels, the quantization levels is the same. Non-uniform? Okay. Which one you expect to be better? Why?
The actual signal. Because it's like your signal is going to be more focused, let's say around 0. So when your levels are around 0, because that will more accurately represent the signal.
Okay. But that's right. But keep in mind also, generally, in optimization, because here we are finding the optimal space. In optimization, generally, the more constraints you introduce, the less optimal solution that you can get. Why? And optimization is just searching for the optimal solution. So assume that I want to find the optimal level. So like I have this space of points and have a certain function. Usually it's two-dimensional. Let's say you want to find the maximum of a function over this, whatever. This is the x-axis, this is the y-axis. So in this region, what's the maximum? If you have no constraints, so you search the whole space. If you start putting constraints, I want whatever, x to be greater than 2. I want the power to be positive. Like very usual constraints in optimization problem communication and in the related field. The maximum power, you have a constraint on the maximum power. You cannot grow your power beyond a certain value. You want your bit error rate to be less than a certain value, and so on. Every time you put a constraint, take a slice from this region and you discard it. One constraint, so this part I cannot search in it. Another constraint, this part I cannot search it. So probably when you plot the signal or the function above all of this space, maybe the maximum value lies on what we call infeasible region, a region that's not feasible, but the maximum is there. Once you slice it, you lose that maximum. You will look at another maximum within the new region that you are looking into it. So yes, and this is exactly the same. Here we put a constraint that we want the spacing to be the same. That's why we ended up with a different numbers between uniform and non-uniform. And since this is a Gaussian distribution, which means I have areas with higher probability than others, because we know that the Gaussian looks like this. So regions around 0 have much more probability than numbers that are far away. And if you go again to MATLAB, just try it today if you have MATLAB. Type rand in. Most of the time you'll get 0.7, 0.9, minus 0.7, minus 0.9, 1, 1.2. Yani you need to do this 1,000 times to get a 5 or a 6. It's very low probability. Yani to get 100, you need to do it 10,000 times. To get 1,000, you need 1 million. So this area has more probability. So if we were doing this for a uniform distribution, I don't need to do optimization. I can just slice it equal regions because it's uniform. So all areas have the same probability. So based on how many levels you want, I'll just slice it equally because all regions have the same probability, and you'll get the best solution. Right. So let's do an example. I think I will do an example. Let's do an example. Design. And this is what you will need to do on Wednesday. To use those tables, I'll give you whatever table if I ask you, a uniform or non-uniform. and then so design a 4-level quantizer for a standard normal Gaussian source. So let's start with the, believe it or not, the non-uniform is easier to do because I'm giving you this figure. So I want 4-level. Where is the 4-level for the non-uniform? This is uniform, this is non-uniform. So number 4. So this is the number of levels. If you want, again, if you want 1 level, it's 0. You round everything to 0. And this is very common. And if I tell you I have a Gaussian source, this is the only thing that I'm telling you, a standard Gaussian source. Design a good estimator. Give me a good estimate for the number that it will generate. What's the best estimate that you will have in mind? 0, the mean of the distribution. Because you don't, it can be positive, can be negative, this with same probability. So your best guess is to use the mean, and this is what we are doing here for both uniform or non-uniform. For uniform, they don't have spacing. It's 1 level. It's at 0. Anyhow, and as you can see, for 2 they are the same. I guess you start to see the difference. I guess at 3 or 4. But let's design our. So 4 levels means that the A's are 0 and 0.916, and the X's are 0.4528 and 1.512. What's those? Those are, because this is your quantizer. This is your input, and this is your output. So the A's are here, and the X's are on the y-axis. So 4 level, I will have something like this. So what are the A's that are on the x-axis? I have 0, 0.9816, and it's negative because it's plus minus. So I'll have the 0, 0.9816, and minus 0.9816. What are the y-axis points? Y-axis points, I have 0.4528, 1.51. 0.4528. ما شاء الله واحد متابع اخبار اوكرانيا شكلكم. 1.51, and then they're negative, minus 0.4528 and minus 1.51. خلاص, you're done. Now you can plot your quantizer. How do you plot it? Exactly the same as in here. So you just follow here. What does this mean? What does this quantizer mean? It means that if you get, when you put rand in, it will give you a number. شباب جوالات لو سمحتوا silent, not on your tables. So if you get any number between 0 and 0.98, you quantize it to 0.4528. Any number between 0 and minus 0.98, you quantize it to minus 0.4528. Any number greater than 0.9816, you round it to 1.51, all the way to infinity. شلون جاي؟
I think it means like why do we go this way, not this way? Like round the minus 9.816 to minus 1.5 plus 1.51.
ويحفظ عشان الرسمه زي السلم لازم تكون مذكور احد اتجاه اليسار.
Because you have to have specific levels at the output. And the output has limited, you have limited number of outputs. You want to round them. Because next step is that I will assign binary bits to each level. So this level will be 0, 0. This will be 0, 1. This will be 1, 1. This will be 1, 0. Okay. So now, for example, if I tell you on Wednesday, your input signal is, for example, your input signal is, when you put rand in, for example, so the input signal, let's say 1.3. Sorry, I don't know how to put my hey on silent. 1.3 minus 0.4. Let's say minus 3.5, 0.12. This is not realistic. 0.01 and so on. Let's be careful. So assume that this is your input. When you sample your signal, this is what you got. How do you round it? So quantized output, let's say, output. 1.3 وين؟ 1.3 هون تقريبا, right? So I take 1.51. Minus 0.4, minus 0.4 somewhere here. So minus 0.4528. Minus 3.5, sorry. Minus 3.5. Minus 3.5 somewhere home بالأخير. Minus 1.51. 0.12. 0.4528. 0.01. 0.4528. What's the coded output now? Coded output. So I have 0, 0, 1, 1, 1, 0, 0, 1, 0. Okay. So this is your coded output, and this is the input that next chapter, chapter 6, will deal with. Okay, we did everything. We have this signal now. How do we process it further? Yes. Yes, I'll have it next. خليني أخلص Okay. طيب. So this is the non-uniform quantizer. So now I tell you what's the error. What's the mean square error? So now the table, if you look at the table, there is a last column in the table. It says mean square error, or this is error due to quantization. Where did you get your error from? Because you, instead of 1.3, they represent it as 1.51. Instead of minus 0.4, you round it to minus 0.4. So there's an error. So if you have large number of input, very large number, and you use four level quantizer, the error that you'll get is 0.1175. How do you calculate this error? So if I ask you in the quiz, calculate the exact mean square error. Mean square error.
1.51 minus 1.3.
Yes, so it's 1.3 minus 1.51 square plus minus 0.4 minus minus plus 0.4528 square plus minus 3.5 minus minus 1.51 square plus 0.12 minus 0.4258 and so on square, and then How many you have? 1, 2, 3, 4, 5. 1/5. So now if you do this using MATLAB for 1,000 points or 10,000 points, the number that you will get is very close to mean square. Yes.
Mean square error. It's the mean square.
Yeah, not the mean square error. It's the mean square error, because into how do you take the mean? How do you take the mean?
Divided by n.
If you have probabilities of each point, you should multiply by the probability. If you don't have probability of each point, so this is the average distance. On average, how far you are from the average square distance. How do you calculate the average square distance? You have to calculate the square distance and average it, right? So if this is the exact, if I tell you what's the approximate distortion, approximate error, this point whatever 11.1175. Okay. Fine. So this is the non-uniform. Let's do the uniform and then go to the coding. How do we assign bits to those levels? What do you mean by the maximum error? Yeah, theoretically speaking, what's the maximum error? For this, or for anyone?
We take the highest input and we see the difference.
For this set, yes, you can. Yes, you can find what the maximum error for this specific set. But theoretically speaking, you can have, for Gaussian, you can have input that's infinity or very close to infinity. So you have very large error for a single one. But this is very unlikely, and that's what I'm saying. When you want to average them, here what we average, we assume that they all have the same probability. This is not the way to average random numbers that are more probable than each other. Yes. So you do it for the 1,000 points and average those 1,000 points. That's how you get it.
So the number B is the mean square error.
No. For each point, it's called the square error. It's not the mean square error. For each point,
It's called
square. This is the square error because the point minus its quantized level. Point minus quantized level is error. Square is the square error. The mean of all of them is the mean square error. Okay. Type. What if we want a uniform quantizer very quickly, because I might ask you uniform or non-uniform, or some of you uniform, some of you non-uniform. Uniform quantizer. So we go to the uniform table. So this is the uniform table. You go to the 4th level. And as you can see, the first thing you can see is that the error 0.1188, which is larger than 0.1175, because this, as I said, we have more constraints, so less optimal. So here we have delta. It's just giving us delta, which is 0.9957. So delta 0.9957. Fine. So how do we plot the quantizer? I have 4 levels, right? I have 4 levels. The distance between them is equal. So 1 level, 2 level, 3, 4, right? This should be delta. This should be delta. This should be delta, right? So I need delta over 2 because this is what This is delta over 2, right? And this is delta over 2. So what's delta over 2? And if you have a calculator. 3? 3? Oh, 0.45. 0.4978, whatever, 78. طيب شباب, so points. طيب if you have your calculator, just add 0.4978 to 0.9957. 0.4978, and this is what? 1.4935. So this is minus 0.4978, and this is minus 1.4935. What's the x-axis? Again, deltas. Delta 2, delta 3, delta, if you have multiple. So here is 0.9957. This is minus 0.9957. خلاص, you're done because you have only 4 levels. So, yes. So, the table. Yes. Yes. مو مايل, معلش كمان هذا نفس الشيء. طيب, I will talk about it. I did not talk about it. Okay. So this is our the x-axis is not giving me the no. This is one level. So this is another level. The levels and distance between levels is just. And why did I extend this? Sorry. Okay. So this should be this. Okay, now if you want to do the same thing, you can do the same thing as the same input, but the values that you will subtract from are different. So instead of 1.51, you have 1.49. Instead of 0.4528, over there you have 0.4978. So this will give you different distortion. Again, if we have large number, distortion here should be higher than the distortion in the non-uniform quantizer. So now how do we assign? And oh, I have, yes, now I have one more example. Sorry. Because this is important. Note, let's note. Note. Because this might be in the quiz also. The tables are given for a standard normal distribution. Normal 0 and 1. If I tell you I have a Gaussian source that has a variance that's not 1, that's 10 or 20 or 50, how can we modify the table? Let's do an example, quick example to see this. So example. So need modifications for non-standard normal. Having non-zero mean is usually uncommon, but it's very easy. Let's design for zero mean and shift it towards the mean. Okay. So the mean is not critical. What's critical is the variance. Example. A certain Gaussian source is sampled at fs equals 200 hertz. And the variance of the source equals 400. So question 1, use 8 level. I will not draw it, I'll just solve it. Use 8 level quantizer. Using 8 level quantizer. What is the resulting bit rate? So I'm giving you the sampling frequency. So you have 200 samples per second coming to you, and you are quantizing them into 8 levels. 8 levels means how many bits? 3. 2 to the 3 is 8, right? So 8 levels means 3 bits per level, or 3 bits per sample. So very simply, so your bit rate is what? 200 times 3, which is 600 bits per second. So the input to this A to D converter are samples with 200 samples per second. The output is 600 bits per second. Fine. Question 2. Using a uniform quantizer, what's the resulting distortion power? What is the resulting distortion noise, or power of the noise? Before that, before answering this, how can you modify the quantizer itself? Fine. So the quantizer is designed for n of 0 and 1. Let's call this random variable x. Okay. Now, if I define another random variable, define another random variable y equals ax. Okay. What's the mean and variance of y? Mu y is what? The expected value of ax, right? If you have a constant in the expectation, can you take it out? Right? You can take it out. So this is a expected value of x, which we know that this is a mu x, and we know mu x is 0. So mu y is 0. What's the variance of y? Variance of y equals variance of ax. What happens to the constant if you take it outside? If you take the a outside, it gets squared. Why? Because the variance, definition of the variance is the expected value of whatever squared minus mu squared, right? So this is a squared variance of x. Okay? So now, which is a squared. So if I'm telling you the variance of y is, so if the variance of y equals 400, this is sigma square y. So then this means that sigma y is 20. It's like I am defining y. It is just like y equals 20x. Very simple. It's like we're defining, if I'm saying, giving you a Gaussian source that has zero mean, but its variance is 400, the relation between this and the standard Gaussian distribution is 20x. So now, how do you modify the table? Very simply, these are x's. هدول with delta are distances for x, which is not standard normal. So if I want to use it with y, I have to multiply it by 20. Each number I have to multiply it by 20 in this case. If I want to design a quantizer for this example. So to design a uniform quantizer for this source, delta nu equals 20 times delta table. So instead now of the distance between two levels 0.99 تضربها ب 20 becomes like 19.5 or 19.8, the distance between the two levels. And the same for the non-uniform. For non-uniform, to design a non-uniform quantizer, multiply يعني بصير هلا whatever a nu equals 20 a table x nu equals 20 x in the table.
Relation between the mean and the variance. So if the variance is like 100 and the mean is, then you have to start from.
As I said, if there is a change in the mean also, keep it in your mind. Don't do anything to the mean. Just modify the deltas if you are doing a uniform for the A's and X's, and plot your quantizer and then shift it to the new mean. If the new mean is 20, I'll shift everything to 20. If it's minus 20, shift everything to minus 20. Because the mean does not change the relative distances, does not change the distance between the levels. It just changes the center. So the mean does not affect your distortion, the mean. Okay? If the new Gaussian has a center of 0. As I said, if I maybe in the exam, the quiz, since this is the day after, I will not change the mean. If I change something, I will just change the variance. So the center is 0 if the mean of the source is 0. The mean is non-zero, again, do everything for a 0 mean and then shift. If I tell you this Gaussian source has a mean of 2 and variance of 1, I can do this. I can do this in the quiz. I change only the mean. So you design, if the new mean is 2, هيصير 2, center instead of 0 يصير 2. This is 2.99. This is 2 minus 0.9. It's 1.111. Whatever. That's all. Okay. No, you change both. Yes. You change both. For the uniform, this is delta. So the new delta is 20 times the old delta, right? The variance, so the last part, you have distortion D. This is the variance. So the new variance is what? So distortion now distortion nu or d nu equals what? Yes, sigma square d table. So for this specific example, اللي هو 8 levels uniform. 1 second, where is it? So n equals 8. So its the original distortion was 0.03744. D table 0.03744. Then the actual D nu or actual D equals 400 times 0.3744. Okay, question? If the variance is still 1, yes, you just shift the x-axis. Yes. Any more questions on this? Oh, yes.
Variance changes. We solve for mean zeros, and then we shift also in the x-axis.
Sure. So shift it. After you fix the variance, shift it to the new mean. Yes, shift the x-axis. Okay. So now the question that, yes. We use what? Yes, you round it up, of course. And you need number of bits to 5, 6 is the same as, that's why it's better if you want to use 8 with multiples of power of 2. But now the question that one of you asked, how can we assign bits to levels? How can we assign bits to levels? Usually there are 2 ways. Let me bring a slide. Yes, this one. We can assign the case of 8 levels, 3 bits. We have 2 ways. We have the natural bit coding and gray coding. Natural bit is just 0, 0, 0, 0, 0, 1, 0, 1, 0. You follow the binary code of the number, which is usually not desirable. What's more desirable is the gray coding. I'm not sure if you did this in any other code. Gray coding means what? The difference of the code between 2 adjacent levels, only 1 bit. Okay? So as you can see, look at each level, 0, 0, 0, 0, 0, 1, 0, 1, 1. This is 1, this is 1. So you change, every time you change 1 bit. Why is that? So in gray coding, change 1 bit between adjacent levels. Make it, you have less errors to encounter. Why? Assume that, let me put another figure, because instead of just plotting, no, not here, I need figure 515 from the book. Okay, this is it. Okay. So assume that here I'm not using gray coding. Assume that once you quantize, you will send those bits. Okay. So we'll send those, and then at the receiver, at the receiver, you'll start decoding those back to the levels because you want to reconstruct your signal, right? So assume that at the receiver, certain level was coded by 1111%, 1111. It went to the receiver. Due to errors in the channel, instead of this one, you got 0. So assume that instead of receiving level 1111, we have an error in the first bit, and then we got 0111. The receiver would think that what's the level? Just the opposite, from minus MP all the way to MP. So huge error. So it will be decoded as MP instead of minus MP, which is a huge error. That's why if different adjacent levels are different only by 1 bit, if any bit flips, you move either to the top or to the one below you. If one bit flips, if you have error of 1 bit only, you move to the level next to you, which is a small error, because different levels usually you don't have. Yani probably we'll talk about this later on, but error are usually randoms. We can encounter what we call burst error. Burst error, if you have series of error, what about just next to each other? This is not very common. The more common is that you have 1 bit in error. And you have different levels, and those bits. And we'll talk about this later, but we'll not send this one as one. We'll group them later on. But again, this idea of gray coding, we'll use it again with modulation. When we assign symbols also, we'll make the symbols, adjacent symbols, differ by only 1 bit, so that if you make an error with the symbol, the whole symbol is wrong, then when you go back to the bits, you have only error in 1 bit. So it's always desirable to use gray coding, which to minimize the bit error rate. What do you mean the highest level? Oh, this table, Hada? You talk about this? Honestly, I'm not sure why. For example, here started from here 0, 0 all the way to 0, but then continued here. I don't know actually. And I always do gray coding, but yeah, probably you start from here, then you go. But to me, I think it will not matter. It will not matter if you, from bit error rate point of view, if you are using MBC coding, it will be the same, as long as unless it's designed here. But here, gray coding, regardless of where you start, yes, as long as adjacent, they are different by only 1. Okay. Fine. I think I can take the absence. Well, let's continue maybe and do the absence at the end. So for the rest of this chapter, which I keep hoping to finish, we'll talk about now what we call PCM, or pulse coded modulation. Pulse code modulation. So we look at the whole. Let me bring a figure from the book also. Shabab, fi question? We call the whole system of sampling, quantizing, and bit encoding as a pulse code modulation system. So converting your signal all the way to ones and zeros. So we call this pulse code modulation. So for example, so here you get your input signal. Talk about the signal system. You have low pass filter. You cut the signal. It's like anti-aliasing filter. You cut it at whatever 3.4, for example, the telephone system. You sample at least twice the highest frequency, quantize, and then you assign zeros and ones to the signal. So as an example, examples. Sorry. What? This is the transmitter. Yes. Of course. The first thing is to cut. Like as I said, speech signal. I'm giving an example now. If you will sample the signal at 8 kilohertz, you want to make sure that no components exist after 4 kilohertz, right? To remove aliasing before you sample the signal. So we call it anti-aliasing signal, anti-aliasing filter. So this is like anti-aliasing filter. So examples of BCMC systems. First one is landline phone, and this is a standard for almost everywhere in the world. The signals is low pass filtered at 3.4 kilohertz. So you cut all components after 3.4 kilohertz. You sample at 8 kilohertz, which is slightly more than double the frequency again to make sure that there's no overlap. And then we use 256 levels quantizer, which is 8-bit. And there are standards. We'll talk about them probably in part of next lecture that before the quiz. So 8 bits per sample, which means that each subscriber is generating. So each subscriber is generating what? So 8 kilohertz, and each one has 8 bits. So how many bits per second? 64 kilobits per second. So this is what your voice signal is ready to be transmitted and combined with others. And in the book, I will not go over that section. The last section talks about the old telephone system and how they combine different subscribers into different, more and more subscribers until you reach the main duct that goes to, and how different systems around the world they interface. Because you have to have a point where if you, at least in the past, we used to call, Qatar used to call the one in the US. So there should be a point in between to make sure that they interface with the speed and the synchronization. They should work with each other. Another example, which is probably more interesting, is the CD. And at least some of you are still using the CD to record the songs. No one? So CD, the CD audio signal is cut at 20 kilohertz because you want to make sure that all you don't want to cut any useful frequencies so that you have high fidelity sound. And then the sampling is done. It's a bit weird at 44.1 kilohertz, slightly more than 20. And there are reasons. I guess there are some added, and they keep I forgot, I read once about it. Forgot why it's exactly 44.1 kilohertz. And then what's interesting is that they use 16-level quantizer. Which means 65536 levels. 16 bits, sorry, yes. Levels. Which means that if you are converting a sound signal using this standard, what was used in the CD, the binary coded samples are generated at, you multiply, it will be 1.4 megabit per second. So now, if you are playing your song, so for each second of the song, how much storage you need? 1.4 mega. So 10 seconds song, 14 mega you need to store it. Whatever. 1 minute, multiply by 60. 1 hour, multiply by 60 times 60. So this will tell you how much storage you need on a CD to store a signal. And again, this is very high quality. 16-bit quantizer is very high quality. Usually, with regular systems, if you want, I was talking about sensitivity of receivers. Usually, if you have 13-bit or 14-bit receiver, this is very high quality receiver. But this we use wireless systems when we want very, very small sensitivity to capture. Okay. Fine. So I think I have a couple more minutes. I think we can. What we will do next is we'll talk about two standards very quickly in PCM quantization that are widely used in worldwide, and we then cover two variants of PCM, which are DPCM and delta modulator. And just to give me a heads up and take the absence, I will not start today probably for those. But this idea is nice. So in PCM, what we've been talking about, we sample the signal, and then we see the level, we quantize the level, we code it, and we send it, ones and zeros. So in DPCM is differential phase, differential pulse code modulation, which is simply, instead of coding the level itself, code the difference between successive samples. Because if we are sampling at a certain rate, the difference between samples is not much. So instead of coding the whole level, you code the difference. And we know the starting point. We agree on a certain starting point. And then every time you receive a signal, you subtract from the previous one, and then what you code is, or what you quantize is the difference, is not the signal. Why is this good? Because the difference smaller. So if you use the same number of level for smaller values, you can have better accuracy, right? And then we'll see if we use really fast oversampling, very much higher than Nyquist rate, we will use just delta modulator. Delta modulator is just, you can look at it as a two-level DPCM. You just use 1 and 0. Very fast sampling, take the difference and then use 1 and 0. If your signal is greater than the previous one, just use 1. If it's less, 0. 1, 0, 1, 0, 1, whatever. And if it's growing, you keep sending 1. If it's 0, you keep sending 0. So we'll talk about those two variants, and that will close this chapter, and we will be ready to move to principles of digital modulation. So let's take the absence. If you hear your name, you can leave. Okay. Sources.